Today we'll carry on our discussion about linear regression models, and before we do that, we going to look at what we covered briefly, what we covered last week, and then we'll see what points we hope to cover today. Last lecture, we gave a very broad introduction about what we want to achieve in this module and why do we do research in economics. We highlight the fact that it's important not just to be able to do econometrics. It's more important to understand why you do it and to be able to highlight you the limitation of whatever method you choose to follow or to apply in your research. You have to be aware of its limitations. So it's important, yes, to understand why you choose a certain methodology or econometric technique. I think it's more importantly is to understand the limitation of your technique. So we talked about different type of research, theoretical papers, empirical papers. We said we would be focusing on doing empirical work, but in the same time we should appreciate the importance of theory. And when we talk about the steps, and I show you where econometrics, where the empirical analysis comes, it comes after identifying your research question. You need to look at the literature, you need to look at the theory, what theory tell us about this, what to expect, how these variables interact with each other, what should I expect before you get your hand dirty and start doing the econometrics. So econometrics comes last, really, okay? So you need to be very aware of these, the sequence. So you need to think about why you're there and why you're doing this. So we started with a very basic model, and as we explained, when I talk about a model, I talk basically about the simplest form here is the single equation model. We have only one equation where I want to interpret the behavior of this variable, which we call the dependent variable y on the left-hand side, and the different or number of factors that explain or may explain the behavior of this y. And what is our task here? This is the population function, remember? And because we can't study the population, we need to look at the sample or draw a sample. And my task here is to estimate these betas. And that's how I differentiate between the population equation, the first one, and the second one. It's based on a sample. And that's why you see the parameters here, betas. I use the small letters to just to show you this is from a sample or based on a sample, not based on the population. So my task is to use whatever method you think it's appropriate and you can justify to estimate the values of these betas, and then based on that you can interpret the relationship between different x's or different independent variables and your dependent variable. So we talked about our magic technique that does that, which is the OLS, ordinary least squared. This is the simplest form, and we explain what the OLS does. So all what we want to achieve here, or the main goal here, is to actually to minimize this expression. Okay, so the sum of the square of the error squared. So and we explain why we don't use just the sum of the error, because we said there will be some positive values and negative values of the error that will cancel each other. That's why we square the. Okay, and because we said this error term, this u term, it's something that you don't know anything about, or you'll never see. It's an error, so you can't really, it's random, you can't see it, you can't expect it, but you still can make some assumptions about its behavior, and that's the point here. So we make assumptions about the error term because we don't know how the error term looks like, so we make some assumptions, and these are kind of desirable assumptions. This is what we're hoping to have in our error term. We made like 7 assumptions, that, and we call them the classical linear model assumptions. We explained this last time, and what we will cover today, we'll touch on one or two of these assumptions today, because since you make assumptions, you need to test whether your assumptions are valid or not, okay, before you jump to any conclusion. And we said if all these assumptions are true, then our OLS estimator is a lovely estimator, is blue. What does blue mean? Do you remember? What does blue stand for? This is like 4 words. Best, linear, unbiased, estimator. Great. Okay? So if everything is lovely and nice and goes as we expect or what we like it to be, okay, then we have a blue estimator. Blue, best, linear, unbiased estimator. So what do you mean by unbiased estimator? Do you remember? We have a population, we draw a sample, we have a value for beta. So we estimate a value of beta. So if you get another sample, would you get the same number? No, you will get a different value. So every time you withdraw a sample, you will get a different estimation. But on average, this estimation should equal the true parameter beta. Okay, and that's what it means unbiased. Okay, so that's one thing. So unbiased means on average, the expected value of your estimator, so on average this estimator will be equal to the parameter, the beta, this one, these betas from the true population. Okay, so how about best? What do we mean by best estimator? Remember when we have different estimators, okay, the one that has the minimum variance, that's the best or the most efficient one. That's what we want. Okay, so we want the best, we want it linear, and I'll explain linear. We'll talk about linearity today. This is the whole lecture about, or most of the lecture about linearity today. And then unbiased means, again, the expected value of your estimator should equal the true parameter, beta. And again, the idea here is that whenever you withdraw a sample, you get a different estimation every time. But then on average, if you take the average of all these, and I'll show you an example today, that should be very close to the true parameter. That's what means unbiased estimator. Anyway, so all these points we covered last week. Just to remind you, the lecture recording now, well, it was there last, I uploaded last week on Hanomics. So you can watch the lecture if you haven't attended or if you want to revise what we covered last lecture. And also just a quick reminder that we do flip tutorials, meaning that what we do in the tutorial you should actually practice. So there are 2 videos related to this week tutorials. Hopefully you have covered them. I think they're 8 minutes each or so. So they're very short videos about how to do different stuff in R. So the first one, how to install an R, how the difference between packages and functions, like very basic task in R. And then the second video is about how to import data using Excel sheet. And we will practice more in the tutorial. Okay? So this is what we're hoping to cover this week in the tutorial, hopefully. Now, could you please log in Socrative? Just go to this, use your mobile phones, your laptop. As we said last week, I want you to bring your devices with you, whatever device you have, as long as it's connected to the internet will be fine. So please go on Socrative. You'll be asked about the room number. This is the room number Echo Swans from Economic and Swansea, so Echo Swans. And I want you to answer the first 3 questions. The first question is just your student number, just to know you. And the second, there are only 2 questions then, question 2 and question 3, and they are related to what we covered in the previous lecture. As I said today, I'll talk more about linearity and OLS estimation. And from what we saw, we have some assumptions about the error term. If these assumptions are valid, if these are true, then our estimator, our OLS estimator is blue. And L here stands for the linearity or linear estimator, and that's what I want to explain today. So we have 2 equations here. This equation is linear and variable. Okay, so if you plot this, probably will be a straight line. Okay, because x here is not raised to any power like more than 1. And if you look at this one is not linear and variable. So if you compare this, because this is x squared, if you compare this to this one, okay, this one is linear in coefficient, so the coefficient betas are not raised to any power. This one is a quadratic function. You can see x squared, so it's not linear in variable, but if you look at the coefficients, it is linear. This one, it's not linear in coefficient. So with OLS, we want to estimate coefficient that equation that are linear in coefficient. So in that case, in that sense, this equation can be estimated by OLS. This one cannot be estimated by OLS. Again, so when we talk about linearity here, so we need to think about two things. There are two different forms here. So linear in variable or linear in parameter. Okay? With OLS, what we mean by linear, remember blue, okay? So that means linearity in parameter. So the parameter is linear. So in that case, this one, it's not a linear function. It's quadratic. You see x squared, but when you look at betas, okay, so they are linear. So this one can be estimated by ordinary least square. This one, do you remember what blue stands for again? Best linear. So what we mean here is this one. Okay, linearity in these parameters. Okay, so betas are linear. So they're not raised. They're very the simplest form you can see. It's betas without any power or anything. So it doesn't really matter what we see here with the x. It's here the most important part. We look at the parameters. So the first equation can be estimated by OLS. The second equation cannot be estimated by OLS, and we use nonlinear, because it's nonlinear parameters, we use nonlinear least square, which is different method we'll not cover in this course. Okay? So what we're talking about is linearity in parameter. Okay, so let's just have an example. We have data stored in a package called POE data. So in R, when we see it in the tutorial, you can load the package and you can load the data. So what we have here, data on income and food expenditure. So different levels of income, how much these households or these individuals spend on food. And this is just a snapshot of the data. This is not all the data, okay? So a good practice always is to know your data. So before jumping to do any analysis, you just need to look at the data first. And a very simple way to look at the data, just to look at the descriptive statistics. At least now I know that, okay, so we have 40 observations in this data set. This is the average for income and for food expenditure. This is the minimum, maximum, the standard deviation. You could also plot your data. And again, we'll see this in the tutorial, how to use the function plot to plot your data. So this is on the horizontal axis, we have weekly income in $100, and this is how much they spend on expenditure on the vertical axis, and this is a scatter plot that explains. So what can you see in this graph? What does it tell you? Is there like an indication of the relationship between income and food expenditure? Yes, I see you doing that, but what does that mean? It's positive, yeah? So that means when higher income or when your income increases, you probably will spend more on food expenditure. Okay, can we say it the other way around? Can we say when your food expenditure, when you spend more on food, you will receive more income? So can the causality go from the other side, the other way? Did we talk about this last lecture? Remember? Yeah, we talked about causality. Comes from theory. So, or you remember the example we gave about the crops and the rainfall. So it doesn't go the other way, yeah? So we may have more crops when we have more. So more rain will cause more crops, not the other way around. Okay? So this is the basic intuition or sense. Okay? With here we need to think about what theory tell us. Theory tell us, well, okay, the relationship goes from, or the causality goes from income to food expenditure. So how much you spend on food, not the other way around. Okay? So anyway, so income here is the independent variable, and food expenditure is the dependent variable. And again, this comes from theory, because R would not understand the difference. So if you put them the other way around, R will give you a result. We'll estimate the parameters with no idea about that is something wrong. Okay? Anyway, so it's you who should tell R what to do. Anyway, so we just plot the data, and this is the very simple model we estimate here. So food expenditure on the left-hand side, we say this is our dependent variable, the variable that we want to explain. And we think that income, or based on theory, we think income is an important determinant of how much you spend on food. And this is just like an error term, as I said, and this is the OLS estimation, and I'll show you how to produce this table using R in the tutorial today. But in general, what we are interested in here is the estimation for these parameters. So beta 1 here is the intercept or the constant, and this is the estimation, and income, the coefficient beta 2 is 10.21. What does that mean then? What does 10.21 mean? Well, the sign is positive, so that means there is positive relationship between both variables. Okay, so when income increased by 1 unit, then food expenditure will increase by 10 point. Okay, yeah. So 1 unit here is $100. Remember, the data is measured by $100. So if you go back here, this is measured by $100. So 1 unit here. So that means if income increases by $100, which is 1 unit, then you will spend 10.21 more on food. Okay, and that's what it tells us. And the relationship seems to be significant at 1%. So that's what we would expect. We expect positive relationship. We expect that food or income is one of the important determinants of food expenditure. So this model is linear. Okay, not just in parameter, also in variable as well, because income here is not raised to anything. It's not log. It's not any other form. It's just it's a linear function. So this is just the interpretation of the parameter which we just said now. If you want to plot the same graph, including the regression line, we'll try to do it, but it should be the intercept, and the slope of this line should be how much? That's the slope. Okay, that's what we estimate is beta 2. Okay, so anyway, this is very simple regression line, and we could actually use this regression line to predict how much an individual or household would spend on food expenditure if we know their income level. So in that example, okay, we know beta 1, this is beta 1, this is what we estimated, this is beta 2. So if we know that somebody received 2,000, so if you divide this by $100, because we know the data is in $100, so that means they would spend, if their income $2,000, that means they spend on food $287. And in R, you could actually, rather than doing this manually that way, in R you can use the function predict to predict for different level of income. So this is how much they would spend if they receive $2,000. This is $2,500 per week. This is how much they would. So using the same model here, we expect or we predict how much they would spend on food. So this is the simplest way you could do it. It's very simple model. So we assume that only income is the main determinant of food expenditure. Obviously, this is not going to be the only one. There'll be other determinants as well. But this was just an example. This code here, so I don't want you to be scared when you see it. This is something we'll learn how to do it. So the idea here is, do you remember what I said about every time you withdraw a sample, you will get different estimation for betas. So these numbers here will be different. Okay? So if I change the sample, I will have a different number. And that's exactly what I did in this code. So I asked R to draw 38 observation every time, okay? And then to estimate the model. And then at the end, I wanted the sum of this. I want this to repeat this 50 times. This is C, 50 times. So I did 50. I drew 50, the sample 50 times. And on average, the beta was 9.89. Okay? It's very close to this one. It's not the same. Here's 10.2. It's just I want to show you that this is how we can say whether the an estimator is unbiased or not. So unbiased is something we want, something good, something a desirable thing we want. So how would we do that? How would we know whether it is unbiased or not? So we have to take a sample, because we have a population, and then you take a sample, you get the estimation. Again, another sample, you get a different estimation, You repeat this many times, and then on average, that one should be, or the expected value of this estimator, which meaning the average of these estimators, the average of all these values should be very close to the true parameter. And that's what I try to do here. I try to show you how we can withdraw different samples, and every time we'll have different estimation, and an average actually is different from the first time we estimated, which is 10.2. It's here is 9.89. So don't be scared. I know the code doesn't look really great, but you'll be fine with this when we do it in the tutorial. So now I want you to go back to your Socrative, and there are two questions. Please answer the question number 4 and question number 5. Do you have any question about linearity? What linearity means? So it's very clear now when we talk about linearity, we mean linear in parameters. So we don't mean linear in variable, okay? We mean linear in parameter. So please answer the next two questions, question 4 and question 5. This is not part of the assessment, so it's just a formative assessment. So if you need, like, I'll give you feedback next time about your answers. But so don't worry, but just read the question carefully, answer the questions. And by the way, this is the same platform we will use for the in-class test from next week. We'll talk about this tutorial, because we'll do it at the tutorial, so during the tutorial time, so I'll explain it when we do the tutorial. But it's exactly the same platform we will use for in-class tests, which is part of the assessment. Okay. So now when we talk about nonlinear relationships, again, so nonlinearity here, I don't mean by, when I talk about nonlinearity today, I don't mean nonlinear in the parameter. So we still use OLS, okay? But we look at different relationships, not linear in the first place, like the example we saw now. So the first thing you can think of here, or something that you can see very common in the literature, is the log linear model. So where you have the dependent variable not in level, it's actually in log form, and that's usually the case when you want to make your dependent variable closer to normal distribution. So again, it's another desirable property that we wish to have. So in that case, what we have here is the log of y rather than y. So log of the dependent variable, but x is not taking the log, so it's just x. So in that case, how would we interpret betas? Remember when we estimated this model here, we looked at, we explained this beta. How did we explain this beta? Okay, so when income changed by 1 unit, food expenditure will change by beta 2, the estimation here, which is 10.2. It's going to be different this time, because now what we have, or slightly different, it's not very much different. So what we have here is because of this log here, so that means a unit increase or unit change in x, okay? That means there will be 100 times beta 2 % change in y, okay? So you see it's different, it's not in unit now, we're looking at % change in y, okay? Not unit change in y, it's percentage change in y. Okay, so that means that's very, very popular with the growth models when we have, let's say, for example, this is real GDP on the left-hand side, and this is the log of real GDP, and on this is T, which stands for time. So you're looking at time in terms of units, let's say since 1990, so 1990, 1991, so you count it 1, 2, 3, 4, 5 till today. So it's just increasing by 1 year or 1 month or one week, depending on your data, and that's how you explain it. So you multiply this by 100, so it gives you the growth rate of GDP, okay? And that's the main difference in the interpretation. So rather than just saying that, let's have an example and use different data set to estimate a log-lin model and see the explanation and what that means. So this is a snapshot of the data, or so this is the descriptive statistics, not a summary of data from the same R package again. What we have here is house prices. So this is the house prices, and the square feet is how large or how big the house is, and this is the bedrooms, the number of bedrooms, bath, etc., whether it has a swimming pool or not. So these are like the description of the houses in the data set, and the number of houses we have here is 1,080 houses. So we have data for 1,080 houses, and look at the distribution of the dependent variable. So here, this is the price of the houses prices, and this is the log of housing prices. Do you remember why we usually use log in the dependent variable on the left-hand side? Do you remember I said that? Okay, to make it closer to the normal distribution. This is normal distribution, normally distributed. Compared to this, once I take the log, it became this more like this side. Now it became more like a linear distribution. So this is like another reason why in most of the wage equation you'll see log wage. So most of the log wage models that try to explain wage, they always have log wage, or most of the empirical research will have log wage. So anyway, so this shows the difference why sometimes we need to use the log of the dependent variable, again, to move from this distribution, this form, to this sort of normal distribution form. So what if what's going to happen now? Okay, if I use this model, the log-lin model, so log-lin means the log is in the left-hand side in the dependent variable. So the dependent variable is in log form, okay? And lin means the right-hand side is linear, so I just use square feet. So this is exactly what I estimated. So this is the equation I'm estimating here. So log of price, and on the other side we have a linear or square feet without the log. So here's the estimation. So how can we explain this? What does this mean now? How to interpret this beta here? This estimation, this number, 0.0004. What does that mean? So a unit increase in x, which in my example is the square feet, you multiply beta by 100. So multiply that 0.0004 by 100, and that will give us the percent change in y, which is the price. Okay, so let's go back to this. Okay, so what does that mean now? Yeah, if this is the square feet is the x, is our independent variable. Okay, so if you have one house with one extra square feet in the size or the area, that means the price, would expect the price to increase by, yeah, so multiply this by 100, so it's 0.04%. Okay, that's exactly how to interpret it. Okay, is this clear? Okay, anyway, so this is just an example of, and this is this is exactly what you said now. That's changed by 1 unit, this changed by 0.04%. So this is the plot, which again is very similar to what we see with the square root. So you see when we take the square feet squared, so it fits the data much nicer. So if you compare this with a linear function where you don't have log in either side, so you will have like a straight line like this or like this, is not going to represent the data as as this one. Okay, so that show you how it is like a nice fit of the data. Anyway, so this is the log-lin model or log-linear model. How about the other case if we have the log on the other side with the independent variable side? So in this case, we have, if you believe that, for example, the amount to spend in food, just going back to the food example, increases faster at lower income, meaning that those who have higher income, they probably will not spend as much on food because, I mean, compared to their incomes, it's actually a very small amount compared to what they receive. And in that case, we will have, it's better to have the log on the right-hand side if you think the curve will look like this. So that means at higher incomes, then the spending on food will become like more kind of like flat line. It's not going to go beyond that. Okay, so in that case, we'll have log income, and how to interpret now. The important thing here is how to interpret that beta. Okay, because do you remember that's my job? My job is to collect data from a sample, use some sort of estimation method to get value of these beta. And based on these beta, I interpret the relationship between X and Y. Okay? And in this case, so we actually divide beta by 100, and that is a result of not a 1 unit change of income, it's actually 1% change. Remember the difference? In this example, we said 1 unit change in the square feet. Okay, in this example, we actually say 1% change. Okay, so 1% change in income. So if income changed by 1%, then food expenditure, or how much people will spend in food, will be this number, whatever you estimate for beta, divided by 100. Okay, so let's see the estimation. So this is what we estimated for. Again, this is a lin-log model, meaning the log is on the right-hand side with X, with income variable. So what does this mean now? So how do we interpret this now? This beta. Remember, see, this is log income. And the dependent variable is just food expenditure, so it's not log. So how would we interpret this coefficient now? Yes? Will lead to what? Yeah, how much the food expenditure will increase as a result of 1% change or increase in income? So you divide this by 100. Okay. So that's the main difference, you see. So it's mainly about the interpretation, how you interpret beta. Okay? And that's what we're interested in, because this is our job, to get an estimation of beta, and based on that you try to interpret what that means. Okay, so this is again plotting the data. This is it's kind of, this is what I was talking about. So if you believe, so this is income, okay? When income increases, well, okay, food expenditure increases, but at some point the graph or the line or the curve become more like flat, because after some level of income, when your income very high, again, you're not really gonna increase your spending on food that much, okay? Because you're very rich, you're actually spending a lot on food already. So if your income increases after that point, you don't expect, you probably would be spending on other stuff, okay? Maybe you'll get a nicer house or a nicer car, or you do something else. You're not actually going to spend more on food. Anyway, so this is how it looks like. Okay, so the third example we look at is, okay, so we looked at the case when we have log on the left-hand side, the log-lin model, and then how we explain beta, how we interpret beta in log-lin model. Okay, so 1 unit change in X, okay, will lead to, okay, so you multiply beta by 100, and that's percent change in Y. Okay, so the other case, when we have the log on the right-hand side, then you divide by 100, and that means 1% change in the independent variable in X will lead to beta over 100, so divided by 100, change in Y. So how about if we have log in both sides? We have log on the right-hand side and in the left-hand side. So we have log Y and log X. Okay? In that case, this is what we call elasticity, which means the percent change again is percent change. Okay? So beta here is going to be, if you increase X by 1%, or if you change X by 1%, then this is Y will change by beta percent. Okay, so the percent change again is percent change, and that's why we call it elasticity. Okay, so in this example, this is the data. This is the demand for chicken, for those who like chicken, and this is the model. Remember, we have log Q, the quantity demanded or bought from chicken, and this is the log price. And the estimation here is minus 1.12. So what does that mean? We'll have a break after this. Just tell me what that means. Yeah? But how much is that change? So if the price changed by 1%, you remember this is log. Okay, then what's going to happen to the quantity demanded or bought from chicken? Is it going to increase or decrease? It's going to decrease. The sign is negative, so we know that. So it's going opposite direction. So when the price increased by 1%, then the demand for chicken will, or the quantity demand from chicken will drop or will decrease by? Is it chicken or percent? It's percent. It's not units. Okay, remember, because we have log in both sides. So percent change again is percent change. Okay, so 1 unit change here. It's not 1 unit change. It's 1% change in the price will lead to this change percentage again point in the dependent variable, which is the quantity demanded here. Is this clear now? So the idea here again, when we talk about linearity, we know what we mean by blue. Linear mean the estimate the beta. So it's the model is linear in parameter, not linear in variables, because here we have a few examples when the model actually is not linear. We actually have log, len, log, and log on both sides. Okay, so these all are linear parameters, and that's why we use OLS. Okay. And now we explain how to interpret, how to explain the estimated coefficient in each one of these cases. That's your task in your research. You collect data because you want to do that. So let's have a break now, 10-minute break, and then we'll come back to carry on with the next point we want to cover today. Okay, in the first half of the lecture, we talked about linearity. What we mean by when we talk about linearity, we actually talking about linearity in parameter, not linearity in the variables. Okay, and that's the important thing. So when it is linear in the parameter, we can use OLS, and we show how to interpret the estimated coefficient in different cases. If we have log len log, or log model. In the previous example, we saw some data that we could actually have something like some variables that it takes. When we look at this data, if you look at the variable pool here, so the minimum is 0 and the maximum is 1. So it seems like a variable that you're actually measuring, trying to capture or measure whether that place or that house has a pool or not. So it's like the answer is yes or no. Okay. So you'll see many situations where you actually need to use this sort of variables, and these variables called indicator variables or dummy variables, where you can, you try to say, okay, so it's like a binary variable where yes or no, male or female, if you want to capture like the seasonal effect or not. So in that case, you will use what we call a dummy variable. So I have an example here where I want to see whether the being close to university, whether the house is close to university, whether that would affect the price, or how much on average houses that are close to the university will be different in price compared to the houses that are not close to the university. So my dependent variable is the price of the house, and the independent variable takes only two values, 0 or 1. So 1 means it's close to the university, and 0 means it's not close to the university. So if you drop this, okay, if you look at just beta 1, so beta 1 here is the average price of houses in this sample, okay? So beta 1 here is just the average price. Okay, but now if you talk about, if you add this and estimate the model, that means, okay, so that means beta 1 here is average price of houses that not close to the university, because that means if this is 0, that means it's not close to the university, so that means beta 1 is the average prices of houses that are not close to university. Beta 2 then, that means it's the difference between average prices of both categories, of both groups of houses. So if you see here how many groups we have in this data, or we're talking about houses that are close to the university, houses that are not close to the university. So how many categories or how many groups we have? 2. How many dummies we have? Only 1. So we have only 1 variable here, okay? And this is something else you need to keep in mind when you use dummy variables. You always have to include G, number of groups, minus 1, okay? So always you have to drop one of the groups. Why? Because this is the group that I compare with. So in this case, when I say this beta 2 here is the average price of houses that close, the difference between the average prices of houses that close to the university to those who are not close to the university. So the group that is not there is actually my comparison groups, the group I'm comparing with. So in that case, we call it the reference group, okay, or the base group. So this is what you compare with. So you always have to drop one of the groups, okay? So if I have G is the number of groups, then I need to use G minus 1. So if I want to put dummies to capture the effect of 4 seasons, so how many dummies I include in the model? 3. So you drop 1 to compare with, okay? Again, so if you want to have, if you have like monthly dummies, so you have how many months we have? Are you sure? Are they 12? Yes, we have 12 months. It's 12, yes. Okay. Okay, so how many dummies? 11. So we drop 1 because we want to compare with. Okay? You weren't very sure about 12. Okay. Okay. Maybe you just follow a different calendar. You have 12 months. Okay. Anyway, so in this case, we just estimated the model. So what does this mean then? 61.5. Again, I'm using OLS, so I didn't use any other method. So it's very simple OLS to estimate this model, this equation. So here, so what does this mean then? What 61.51? Okay, so so any try? So just try. Just what does that mean? So let's go back here and just. So beta 2 here, okay, is the difference, okay, in price between the houses that are close to the university and the houses that are not. You remember my comparison group, all those houses that are far away from the university. So that means on average, a house that is close to the university, on average, the price is 61.51 higher than a house that could be pounds or dollars, higher than a house that is not close to the university. So this is the difference between both categories. Okay, so on average, the house on that's close to the university will be higher. The price will be higher than the house that is not close to the university. Okay, so okay, so this is the dummy variables. Okay, go back now to Socrative, and please, there are two questions. Answer question number 5, question number 6 and 7, please. Okay, so let me just summarize what we said so far. The first half in the lecture, we focused on linearity and what we mean by linear models. So linearity here, when we talk about linearity, we talk about linearity in parameters, so we don't mean really linearity in variables. This is one thing. The other thing is that now how to add a dummy. Sometimes you have different categories or questions that are answered by yes or no, okay? Or different, let's say, genders, male and female, and you want to see the differences, whether there's like a wage discrimination between male and female, so you want to see like any differences between two individuals in wage, between two individuals that have the same characteristic, but maybe they have different gender. So you compare males and females, so whether they would receive different wage or not. So this is the sort of dummy variable that you'd use, and again, the most important part here is how to interpret that beta, the estimated coefficient, and also, okay, to avoid adding the number. So the number of dummies they use has to be the number of group minus 1. So you have to drop always one group to compare with. Okay, so this is okay now so far. We want now to turn to the tests. If you remember, we made some assumptions about the error term. Okay, you remember the 7 assumptions? Okay, we now want to look at these assumptions. If I go back to these assumptions, that was from last lecture, and we started with this in this lecture. So if you look at these are the assumptions we made about OLS, about this model. So first model is linear in parameter. We already know now what we mean by linear in parameter. Okay, one of the and I said these assumptions, if these assumptions are valid, then our OLS estimator is blue, best linear unbiased estimator, and we explain what that means. So because these are assumptions you make about something that you don't know, which is the error term, you need to test whether these assumptions are valid or not. So this lecture and the next lecture, or the rest of this lecture and the next lecture, we'll be talking about diagnostic tests, how to actually test for these assumptions, whether they are valid or not. So what I wanted to start with is a very simple assumption here, which is the assumption 6, that there is no multicollinearity. So I want to explain what that means. Okay, so next time we will probably cover 2 or 3 more assumptions and how to test for whether these assumptions are valid or not. So in the next part of the lecture, as I said, so we'll just focus on multicollinearity and what that means. So as I said, this is assumption 6. No exact linear relationship between or among x's or your independent variable. Okay, so these x's should not have linear correlation or linear relationship, okay, among any of these x's. So for example, if x2 plus 3x equal 1, that means I have perfect collinearity, because you can express one of them as a linear function of the other. So here x2 from there, so here x2 equal 1 minus 3x3. So in that case, you can't really include both variables. You can't include x3 and x2 in the same model. Okay? Why? Because there's perfect collinearity between these both. So just for example, if you put, like a silly example, of course, if you put income variable twice, measured in dollars and measured in cents, so it's the same variable. Okay? Or here, what I was talking about a minute ago, 2 minutes ago, what we call the dummy variable trap. If you included the constant, this one, and you have 2 groups, for example, and you included 2 dummies. So remember, so what is the rule of thumb we said? G minus 1, number of group minus 1, number of groups minus 1. Okay, so we have two gender, female and male, so I need to have one dummy. I have 4 seasons, I include 3 dummies. We have 12 months, I include 11 dummies. So I always drop one. So if by mistake you included this one, the intercept, plus G, the number of groups, that's called the dummy variable trap. And that means you have perfect multicollinearity. And most softwares will actually not estimate the model. I will tell you there is a problem. And some of them, like Stata, they actually drop one variable. They choose to drop one for you, one group for you. Some others will just give you an error message. I think eViews wouldn't. Will just give you an eView, an error message, and it's not going to estimate the model because there's perfect multicollinearity. Okay, perfect collinearity between 2 or more variables. Okay, so as I said, this is like a very rare case. It's not going to be like very common in practice. It's usually like a mistake, something you do by mistake, by including like by falling in a dummy variable trap, or including a variable like income measured once by dollar and then measured again by cents. So something that is done by mistake. And as I said, this is not something you will actually encounter in practice. What we what we see in practice actually is imperfect multicollinearity. So there's sort of correlation between the variables, but this correlation is not 1%, is not 100%, is not perfect. So it's somehow high or to some level. So for example, in the same example here, or very similar to what we discussed in the previous slide. So I have x2 plus 3x3, but there's some sort of random term here, okay, equal 1. In that case, okay, you can express this as a linear function of this, okay, but there's some sort of random element here because it's not 100%, or the correlation is not 100% between both variables. And in that case, we have imperfect collinearity between x2 and x3. And unfortunately, this sort of multicollinearity, that's what you don't see, okay? So as I said, the first one, it's not a big problem because most software will warn you, okay, will tell you there's a problem. Some of them will not even estimate the model, okay? But in this case, you will have an estimation, and we will see now what will go wrong. So if there's imperfect multicollinearity or multicollinearity that's not perfect, we will estimate the model and we will get estimation. And what will be the problem with this estimation? Well, your estimator will still blue, best linear unbiased estimator, but you will see, although you have high R square, which means you have a good model, or indicate that you have a sort of good model or K model, okay, you will have most of your coefficients are not significant. So even if you expect significant relationship between, or statistically significant relationship between 2 variables, or theory tells you that there should be, the price should affect the quantity demand, the income should affect consumption, okay, or education should affect how much earning or wage you receive. This is all what we learn from economic theory. And then we use data, estimate the model, and then, oh, actually, there's no relationship between these variables. So there must be something wrong. And it is likely to be because of multicollinearity, because one or two or more, of your variables are correlated. So in that case, as I said, you will see high R square, but mostly insignificant coefficient. And your coefficient, your estimated coefficient, would be very sensitive to the data. So if you change the size of your sample, you'll see massive change in your estimation. So, and that is the problem. And the case here, the problem here is that if you have 2 variables, 2 x's or 2 of your independent variables that are correlated, in that sense, in that case, it's really difficult to isolate the effect of each one on y. So it's very difficult to estimate the impact of each variable separately on y. So how to test whether I have multicollinearity or not? So we agreed now that perfect collinearity is very rare. It's not going to happen very often. It's usually happen by mistake when you include, and as I said, your software might actually warn you about it or even not estimate the model. But the problem is with imperfect collinearity, when I have some sort of correlation or high correlation between, it's not perfect correlation, but still there's correlation between 2 variables. So how to detect for this? There's no unique test, but there are some signs or symptoms that you can see in your estimation. We already highlighted one of them when you have a high R square but few significant coefficients. So when you have high R square, you actually expect that you have a few or more of your coefficients to be significant or statistically significant. That means your model explains much of the variation in the dependent variable. But if it doesn't, then that means that's like a sign that you have a problem with, you might have a problem with multicollinearity. You could look at the correlation between x's, okay, and see where the problem comes from, which two of your variables that are correlated. Or you could do some sort of auxiliary regression where you actually regress one of the x's, the other x's on one of the x's, the one that you suspect it's causing the problem. Or you could look at something called the high variance inflation rate. So let's not just talk about it. Let's just see it in practice. Let's see some example of where we have collinearity or multicollinearity. I'm using data here that has, this is just a snapshot of the data. This is not all the data. So the variables I have here is education. So number of years of education. So this individual, number 1, has like 8 years of education. This one has 9, 12, etc. So this is the number of years of education. This is dummy variable, whether they live south or not. Okay, so that means 0. That means they don't live south. Female means if there's 1, that means the person is a female. If there's 0, that person is male. Experience. These are years of experience. So this person the first person is a female and she has 21 years of experience. Union, whether they are member in a union or not, so it's yes or no, so 0 or 1. Wage, that's how much they receive. Age, their age. Race, occupation, sector, whether they are married or not. So they have like this data, and I think it's 540 observations, and we want to fit a model that explain differences in wage or what factors that determine wage, believing that these are the factors that are important in determining wage. So what I did, as usual, I said, just look into your data. So these are the descriptive statistics of the data. As I said, yeah, it's about 534 observations, mean and other statistics. So what I want to fit here, we agreed that usually with wage, the log wage or the log lin model is much better than just than lin model. So we have here log wage, and I put all the other variables on the right-hand side. And, well, from theory, we understand that if you have more years of education, you should earn more. If you have more experience, you should earn more. If you older, probably should earn more again. So these are variables that can, and of course this would be different if you are a member in a union, or different to the sector or what type of occupation you work, where you work exactly, whether you live south or north. So these are other variables that can explain wage. So when we estimate this model, these are the results. So what's the problem in these results? Is there any issue with these results? First of all, let's look at the coefficients we estimate. Most of them are not significant, or at least the education. This is one variable that we definitely expect that if you have more years of education, okay, you should earn more, okay? Or experience, look, experience is not significant, okay? It's not statistically significant. Age is not significant. Whether you are married is not really important or not, so, okay? So what is the issue here? And look at the R square. R square here is 0.32. Is this high or low? Low or high? So how much R square? So it goes from 0 to 1. So 0, that means your model explains 0 of the variation, 0% of the variation in your dependent variable, in this case is wage. If it is 1, that means your model explain 100% of this phenomena or this variable, the variation in this variable. Okay, so 0% is very low, high percent is really, yeah. So when you have 0.3%, that means this model explains 30% of the variation in wage. Is this high or low? Are you sure? Okay, here's the thing that you should really learn about the R-square. Okay, so it depends really on what sort of what sort of data you're dealing with. So you remember last time when we talked about, we have 3 types of data. So if you compare cross-sectional data, time series data, and panel data. So if you compare time series data with cross-sectional data, okay, with time series data, you would expect the R-square to be really more than 80%, sometimes 90% or more. Okay, with cross-section data, you actually have a large number of units in one point in time, so there's no variation over time. So actually looking across units, different units, and because there's so much heterogeneity, mean that these individuals, there's so many characteristics that you're not picking up there. It's actually 30% is really high. Okay, so in general, the R-square with cross-sectional data would be much lower than what you would expect with time series data. When you have time series data, so you look at the variation over time, so actually you're picking up much of the variation, and that's why you get more than 90% in most cases when you do time series data. But because we have cross-sections here, we're actually comparing individuals, okay? So there's so many characteristics that we're not picking up. So when you look at 500 people, okay, there's so many things that can affect wages that are not there, are not in this model. And that's why, in general, with cross-section data, you might find R-squared 10% and people publish in really high journals, top-ranked journals, and that's actually acceptable because we know that with individuals, different firms, different units, whatever these units are, could be firms, could be individuals, households, whatever, they actually, there's so much of their characteristics that we do not observe, and that's why it's not there, and you can't, it's very difficult to control for everything. Okay, and remember the cross-section data, we look at these individuals in one point in time. Okay, so you don't pick up the variation over time, you're actually looking at the variation across units in the same point in time, which is very difficult. So there's so much of the variation you're not picking up because of that. It's just the nature of your data set. So what I want to say here is 30% is really high. Okay, because these are cross-section data. Okay, so don't just think about, okay, 30% is low because it's supposed to be 90 or 80, that would be high. It's just the nature of the data we're looking at here. This is cross-section data. If it was time series data, okay, I would definitely agree with you. This is really low for time series data, and it wouldn't be even acceptable for time series data. With time series data, you go above 90% very easily if you put any 1 or 2 variables. Sometimes even if you even like regress the variable in its value, like in the previous time, like t-1, you will get 99% R-square. So it's 100% acceptable and expected. But 30% in time series data is not acceptable, is not really expected at all. But with cross-section data, again, because you look at a number of individual, large number of individual, some data, this is only 500 or 540. In some data, you work with 20,000 individuals. You have data about 20,000 people. Do you expect to really put variables that pick up all the characteristics of these 20,000 people? No way. Okay, so it doesn't really matter how many variables you include in the model. Okay, so in all cases you will have really low, relatively low compared to time series, relatively low R-square. So anyway, so this 30% is really high because we have cross-section data. Okay. Yeah. Well, panel data you actually pick both together, so it shouldn't be that low like this one. And it depends. When we talk about panel data, we'll talk about long panels when you have T is really long, and short panels when you have really. So these are different situations. So we'll come back to this and talk about it. I think it's week 7 or 9. Anyway, so at this point now, let's just think about cross-section data. We understand that the R-square is actually what we see. 30% is really high. It's not that low at all. Okay, so that means our model should be picking like 30% of the variation in wage in our dependent variable. But in the same time, we see that most of the coefficients that we expect to be statistically significant, they are not. Okay, can you guess why? Can anyone guess why? Just look at the variables we included in the model and tell me where the problem came from. Do you expect that any of these variables are correlated with each other? Okay, how about if we calculate the correlation matrix? Let's have a look. How about the experience and age? How much is the correlation between both? It's nearly 98%. See, it's from 0 to 1. So it's very highly correlated. And this is something you would expect or not. Experience and age. Okay? So you get experience when you get older, you get more experience. So these two variables are really highly correlated. Other variables, they're not really much correlation. Okay, so this is 0.002 with education. This is 0.09 with age, etc. So it seems that these two variables are causing the problem, experience and age. So another way, so this is one way. Okay, so one way is to look at the correlation matrix between your x's, your independent variables. Remember, I didn't put all variables, by the way, just so I wouldn't be able to fit them all in the slide, in one slide. But I put the most important variable that I suspect there's correlation between them. Okay, so there's like, I don't know how many variables, there's about 10 variables here. I included in this correlation matrix only 5 variables. Okay, so you can actually try other variables as well, but these are the most important ones that actually age and experience are the main cause of the problem here, because obviously you would expect, I mean, it's normal to expect that experience is correlated with age. Is something that we would expect. So this is one way to actually check whether you have or detect for the presence of multicollinearity. Okay, so just by looking at the correlation matrix, you could also do some auxiliary regression where you regress these two variables on each other. So here I regress experience on age. Okay, and obviously it's statistically significant. And how much is R square? It's like 96. It's really high. Okay, my point here is, like, when you talk about this variable here is really correlated with experience. There's another way you could do it, which again, this one I'll show you how to obtain this, which is the variance inflation factor, how to calculate this in R. When you look at this, you will see experience. If you have this, there's no really clear-cut answer where you look in which value above which you will have a problem, but usually most people look at anything from 10 and above. That means there's an issue of multicollinearity. So you'll see these all like 1 point something, except experience is 30.nearly 4, and this one is 31.1.8. Okay, so it's very obvious that these two variables are causing the issue of multicollinearity. So how do we deal with this? To deal with multicollinearity, how to remedy for multicollinearity. So now we saw an example, okay, that having both variables, age and experience, together in a model that explains wage actually is causing a problem, is causing multicollinearity, and that's why we see high R square that our model should seems to perform okay, or to perform well really compared to how high the R square. It's really high in cross-section data. But at the same time, we saw that most of the variables that we'd expect to have a statistically significant impact on wage, they are not actually statistically significant. Okay, and that's again because we include these two variables in the same model. So what do we do now? So, well, you can't do much really. You need to drop one of those variables. And sometimes people ask me which variable to drop. Well, it depends really on your research question, what you're interested in. Okay. Another way to deal with, which we'll not cover in this lecture, and I'm not sure, I don't think we'll cover it in this course, but if we have time, I'm happy to look at it if people are interested in it, is the principal component analysis, where actually you put these variables together and you create like another variable which is not correlated with each other. So this is something we're not going to cover. So I'm going to look at the first solution, which is to drop one of the variables. So either age or experience. Let's drop one of these variables and see what will happen. So here the first estimation without age. So I dropped age. Let's look at education. Remember, education wasn't statistically significant. Now it is statistically significant. Experience wasn't statistically significant. Now it is statistically significant. And we still have the high R-square we had before. Okay, so if you compare this estimation where actually most of the variables are statistically significant as we would expect, if you compare this to our first estimation where the important variables that we expect them to be significant, they are not. Education is not significant. Experience is not significant. Age is not significant. So these all are variables that we expect to affect or to explain the change in wage is actually, or the level of wage, they're not. And the main problem here comes from the fact that you have two variables, age and experience, that are collinear. Okay, so I estimated the model without age, and then I thought, okay, well, let's see how the model will behave if we drop experience instead. It was the same. Okay, everything is significant, all the variables are significant, all of them except only one, the first one. Okay, so they all are statistically significant as what economic theory tell us, and as what we would expect as well. Okay, so the main problem here was multicollinearity, was the collinearity between both variables, experience and age. So what is the problem here again? So again, just to sum up the story, so collinearity or multicollinearity means that there's no, it's one of the assumptions, assumption 6, A6, that's what we assumed about the our model. So there's no exact linear relationship between or among the x's, okay? And we said, okay, perfect multicollinearity is very rare, so you're not going to see it very often. It happened by mistake. But imperfect multicollinearity, when you have two variables that are correlated with each other, the correlation is not 100%, but they are highly correlated. And we saw here very clear the example wage and experience and age. So how to detect for multicollinearity? How to check whether you have multicollinearity or not. So the main symptom here, like the main thing that you can notice, is you have insignificant coefficients, but you have very high R square. Okay, so you have high R square and at the same time insignificant coefficient, which is something, it doesn't really make sense. Okay, so if you have high R square, you'd expect to have significant coefficients. Okay, you could look at the correlation between your x's, your independent variables, as we did, and we found that the correlation between age and experience is 98% nearly. Okay, it's very, very high. And we also calculated the variance inflation factor, and we said above 10 there's definitely a problem, from 10 and above definitely a problem, but some papers will actually consider 7 and 8 still high variance inflation factor. So again, you look at these variables and see which one is causing the problem. In our case, when you look at the variance inflation factor, it's very obvious here. These are the highest ones, the experience and age. When we drop these variables, that's the solution. Then drop one of the variables and re-estimate the model, and it seems to be working and is much better than the first estimation we got. Okay, so now we understand that was the main problem. So this is everything we cover in the second half of the lecture. Just to remind you, in the first half we talked about linearity, what we mean by linearity in OLS, and we show examples of linear in parameter, but non-linear in variables, log len and len log, and said we show how to interpret the coefficient in each one of these cases. And then we talked about multicollinearity, the concepts, the consequences, the detection, and how to deal with multicollinearity. Next time I'll be talking about the other diagnostic tests. I'll be talking about heteroscedasticity, autocorrelation, and model specification. That will be next week. Do you have any questions? Any questions? Okay, so please go back to Socrative, okay, and answer the last 3 questions. I want you to rate the lecture from 1 to 5. 1 is very boring, don't come back. We don't want to see you again. 5 is amazing, somewhere in between. So from 1 to 5. And just tell me, please, what do you like and what improvements you'd like to see in the lecture. Please be open about everything, it's fine. Anything, I read all the comments, and I actually act based on your feedback. So I would really appreciate your feedback. This is one of the most important things to me, because that show me what I need to do more and what I might need to stop doing next time. So please tell me your views. Tell me what you think about the lecture, and rate the lecture from 1 to 5. And just leave a few comments. That would be very much appreciated. Okay, so please don't go before you do that. So if you finish with that, that's fine. Feel free to go, and I'll see you at the tutorial. Okay? Any questions before you go? Okay, thank you so much. I'll see you at the computer lab. Thank you. Please don't go without finish the survey. Thank you.